Now let's digress for just a minute to the idea of polar coordinates. Now, in your prerequisite courses, you should have dealt with polar coordinates both in a pre-calculus or analysis class and in a calculus class, but this is a topic I find that people are often ill-prepared for. It might have been a while since you've seen it. So if polar coordinates are r and theta, that simply means there's a pole which we identify with an origin and an r-axis. This is called the polar axis, and I suppose I probably shouldn't label that r, so this is just the polar axis. Now, r is the distance of a point from the pole. Theta is the angle made by the radial line from the pole to that point with the polar axis. Typically, we're going to let the polar axis coincide with the x-axis, and theta will be the angle as measured counterclockwise from the x-axis. This gives us a relationship between the polar coordinates r theta of a point and the xy coordinates of that point. Now, if we have a vector function, this vector function can be described in terms of the changing distance of the point from the pole. Now, in the preceding, we saw how the distance between the t argument and the t plus delta t argument of our function resulted in an increase in the distance. So r of t can increase or can decrease or can stay the same. Theta, the angle, is also a function of t, and that's the direction of our radial line. So if there's a point out there someplace, and here's our pole, and we're tracking that point, let's say by keeping it in the sights of a rangefinder, okay, this angle is constantly changing. Now, we don't know what's necessarily happening to the distance of that point, but we can see how the angle can increase, decrease, and so forth as a point follows a path. So that theta is the function that describes the direction of the radial line, the angle made by the radial line with the polar axis as a function of time. Now, x of t is pretty easily seen to be just, if the polar axis is identified with the x-axis, we can project down here at a right angle, and our x-coordinate will just be this. And x of t, we can see from this triangle, is equal to r of t multiplied by the cosine of theta. Now remember, r and theta are both functions of t, so we're going to write this as r of t cosine theta of t. Y of t, similarly, is found to be r of t times the sine of theta of t. And this should be no surprise to you. Let's just preview something. If I take the derivative of x with respect to t, what am I going to get? Well, x is a product of two functions. It's r of t times the cosine of theta of t. Using the product rule, x prime of t is going to have to be the derivative of r of t prime times the cosine of theta of t plus r of t times the derivative of the cosine of theta of t. Now, the derivative of the cosine of theta of t involves a chain rule. That's going to be theta prime of t times the negative sine of theta of t. Here we don't have a chain rule to worry about. We just have the derivative of r with respect to t times the cosine of theta of t, whatever that is. Similarly, y of t is going to have a derivative with respect to t that needs to be calculated using the product rule. And part of that product rule is going to involve taking the derivative of the sine of theta of t, which is going to be which is going to involve the chain rule.